layer. It's called a pinch-off, but we don't have to really worry about pinch-off for now, for this lecture. We can come back to that later. So what I'm trying to say here is, look here. Of course, after spending VT amount of voltage, your VGS is going to be effective here. But as you go down here, you have a VGD term, correct? VGD gives VG minus VD, which is, say, for example, 1.0 volts minus 0.2 volts probably. So 0.8 volts, okay? I'm just giving this to you as an example. So here it's 1 volt, but here it's 0.8 volts, correct? That means there's a gradient. There's a change in voltage, okay? So let's consider an electron right at the center, maybe. Or maybe at a distance of x from this place. Okay? So because there is a change in voltage, let's say the effective voltage here for the electron is VGS minus VT is okay. But since it is at a distance x, let's call it Vx instead of Vd. And if it was here, we could have called it Vd. But if it's in the middle, let's call it Vx. Okay? So now, your QD is going to be what? W times Cox, VGS minus VT minus V of x. Correct? This is the effective charge for an electron that's at a distance at the distance x. Okay? Now let's keep that there, and let's go ahead and do a small. Let's go and deal with the velocity factor here. We did have QD times V, correct? Where V is the velocity. Now let's change to red or something. Okay. Now, velocity, as I told you, again, consider the classroom case, depends on the mobility, correct? And also the field of electricity in that channel. The electric field. Okay? And since we're talking, of course, here for QD, we need to have a minus sign. Why? Because we're talking about an NMOS where electrons are the major carriers. So the charge carried by electrons is negative, so it's a minus the whole thing. Okay? Let's come back to this. Okay, so this is mu n times the electric field, the velocity. When you look at electric field's definition, it is given by the negative derivative of the potential with respect to the distance. Let's just substitute that here. V equals mu n times minus dV over dx. I just brought this minus here, okay? Nothing to worry about. Let's go ahead and substitute this value and this value in the equation for current, and let's see what we get. So we get I equals minus times minus becomes plus, so we have a mu n times W times Cox times VGS minus VT minus Vx, V of x, times dV over dx. Isn't that long? But don't worry, it's a very simple equation. And the best part is you know where it came from. Alright, let's go. Let's now take this, whoops, I don't know where it goes, the dx to this side. So it becomes I dx equals mu n W Cox VGS minus VT minus Vx times dV. Always in physics, maths, or any sciences, whenever you have a dx or a dv and you're trying to look for an equation, you want to get rid of those dx and dv's. So what do? You integrate on both sides. Alright? Now what is dx? It's a small distance, correct? In the channel. You remember we took a particle at distance x. So dx is just a small distance of the same thing. So if you want to integrate dx, where would you integrate it from? From the source to the drain, correct? And what is the length of this? You start at 0 and you end at L. L is the length of the channel. So your integration limits go from 0 to L. On the other side, we have a voltage, dV. Okay? So let's see what we are really targeting at. So here, let's try the channel again. So here, you have a zero effect of VD. What is changing? Basically, in your channel, your channel is this way because of the VD, correct? So you integrate from 0 to VD. But we call it VDS, but it doesn't really matter because the source is anyway grounded. Okay? Grounded source. So you're going to integrate your voltage from 0 to VDS. Okay? Alright, now let's integrate, which is very simple. Don't have to worry about anything. Here, I is a constant, so it comes out of the equation, and you have 0 to L. Here, mu, n, w, c, ox are all constants. So, since this is Vx, we could, let's team this VGS minus VT with, on one side, minus Vx on the, as another term, going from 0 to VDS. Okay? So dx, the integration of dx is x. From 0 to L gives you L. I times L. Mu n w c ox. What do you got here? You got VGS minus VT times VDS minus VDS squared times half. That's your basic integration. Okay? Now we're almost there. It's just a rearrangement of terms that all is required here. So I can be finally given as mu n times c ox times w over L VGS minus VT times VDS minus half VDS, the whole square. Square. My dear friends, you have finally derived the most important equation of all time in analog CMOS circuit design. Congratulations! And if you see here, it has all the equations. It has all the terms that we spoke that it would have. It has a mobility term, it has a capacitance term, it has the W, it has the L, it has the effective voltage. Right? It just looks longer, but it's the same thing. Alright, congratulations. So just one more thing we should see before we can sign off of this lecture is as I told you, the MOSFET has a few regions of operations, saturation, triode, and all that stuff. So in saturation, it is seen for different VGSs, the highest amount of current flowing through the MOSFET is when VDS equals VGS minus VT. How to prove this, we'll do the next lecture, but for now, you just look at how your equation would look in saturation, when your NMOS is in saturation. So you just substitute VGS minus VT for VDS, and what you get? Mu n C ox W over L. Let's work this over. VDS is going to become VGS minus VT, which times this is going to give you VGS minus VT the whole squared, minus half of VGS minus VT the whole squared. Right? So 1 minus half is half. So you're going to have half VGS minus VT the whole squared. Take this half and put it here. Half mu n C ox W over L, VGS minus VT, the whole square. This is the equation of current flowing through a MOSFET, or an NMOS, when it is in saturation. Whew, you have finished.